So welcome again. We are doing the acids and bases. And again, those of you who are here, I just ask that you keep yourself muted, but you can ask questions, especially, please do ask questions. So I begin with an introduction to acids and bases. And I wrote some notes to myself. And I'm assuming you guys can see okay? What I see on mine, I'm seeing shadows of myself, but we'll deal with that. I wrote some notes to myself. One was a favor to ask. About half of you, when you come to office hours, you are putting your video on when you're asking me questions, and that is actually very helpful to me. And then about half of you are not. And I know there's a couple people who talk to me and they don't have a camera, but it's sometimes awkward to be talking to a black box. And so I kind of feel it's an etiquette thing to actually turn your camera on during office hours when you're wanting to converse with me. And so if you're able to do that, that would be lovely, that we can actually kind of talk eye to eye. And the other thing, which I always ask in the summer, is to make sure we all know what is due the day we're talking about, which is today, which is your first study set and your first worksheet. And then, does anybody know what's due tomorrow on Thursday?
Map.
You'll have to push your thing. Somebody must know.
Is it our map?
Well, I know. Your Le Chatelier's lab. So your first lab will be due. And that involves, there's links in the lab that you'll go and watch a video and then answer questions. And I'll be in my office hours at the usual time. All right. So usually I have interactive time here. I actually did a recording for your lab that's due on Monday, which is the cabbage juice lab. I did a PowerPoint where I went over a lot of this stuff. And because my hope had been maybe some of you would watch it before this. And some of this I will go over more tomorrow. Today I wanted to get us through some of the basics, which is an ironic use of the word, right? Using acids and bases, because I know some of you will start moving on to the next study set. There are a couple different definitions of acids and bases, and I'll go through those more tomorrow. What most people think of when they think of acids and how you're classically taught them is acids have the hydrogen ion and bases have hydroxide, and that comes from spontaneous. That is the basic definition, the classic definition. We're going to go with a definition that will work for more pieces, and has to do with what the hydrogen ion really is. And when Spontaneous came out with his definition, which was just before the turn of the previous century, around 1897, it was before they knew about subatomic particles. So it was right when we were on the edge. I think it was 1903. Well, it was about the same year, actually, J.J. Thomson discovered the electron. What a hydrogen ion is actually, it is a proton. And so if you remember hydrogen normally is no electrons. I'm sorry, no neutrons. 99.99% of hydrogen is H1, protium. And when you get that plus charge, you have no electrons. And so it is just a proton. The other problem with this classic definition is it assumes you're in water, which is a great assumption because you and I are water-based, and so is this planet. But the definition we're going to go with is Bronsted-Lowry's definition. And so what they define an acid as is a proton donor. Means it will donate hydrogens, ions. And so a base, so this is like the yin and yang. My first year in acupuncture school, I wrote a whole paper about the yin and yang of chemistry, because it was also when I was started teaching here, that a base would be a proton acceptor. So it's accepting the protons. And I'm assuming you guys can hear me okay, because nobody said anything. But
Good.
So it's taking in the hydrogen, and we're going to do some equations, and so you'll see that. So we're going to be looking at the hydrogen ion. And then there is also another mistake with this, something that we're going to refine here, and that is when you lose the electron, you have only the nucleus there. This is why acids and bases burn us when we get them on our skin, that they eat away at metal and things like that, because it's a proton looking for a new home. That it doesn't actually donate the proton. What it is the water pulls the proton off. So if you have something like HCl, this is a very polar bond. So when you learned about bonds, this is actually a covalent bond. It is not ionic, but the chloride, the anion's always going to be pulling on that bond, or the non-metal is pulling. And you actually need the H2O to pull the hydrogen off. So you're always going to have the reaction's going to have to be in an aqueous environment. And what happens is you don't end up with hydrogen ion. The water combines with the hydrogen ion, so you actually get this ion, and then the chloride. And this is what we're going to be writing in our equation. So instead of writing the hydrogen ion, the correct way is hydronium. So the water actually has to pull the hydrogen off. The acid doesn't actually donate it directly. It doesn't come off on its own. And so this is hydronium. And when we get into the math in a little bit, instead of calculating hydrogen ion, it's always going to ask you to calculate the hydronium ion, because chemically that is the more correct way of talking about it. So that's just a quick introduction to some of the terminology. Some other things that it talks about on this page, when we think of acids like HCl, there's, and bases, we often think of hydroxide. Those would be when you're talking about inorganic. So when we have organic acids, which is the vast amount of chemistry in our body, we're organic being. An organic acid is going to have carbons, hydrogens. So this X and Y can be any number. And then you're going to see COOH. That double oxygen is important. And so the carbon and hydrogen part, this is non-polar. And that's the other thing I wanted to point out. Just because something has a hydrogen does not make it an acid. It has to be a hydrogen that is very polarized. And so that hydrogen can be pulled off. Carbons and hydrogens share beautifully. They're like a match made in heaven. And so these hydrogens are not going to come off. Hydrogens that are attached to a double oxygen like that, they are definitely, you can pull them off. And that is because what this really looks like, it's not two oxygens in a row, it's actually a double bonded oxygen, and then this H is on one of the oxygens. Oxygens are very greedy for electrons. They have a high electronegativity. And that double oxygen means they're really pulling the electron. So this makes this bond extremely polar. And so this hydrogen is the one that is donated. So whenever you see a compound with carbons, hydrogens, and then it's ending with that COOH or COO, is what my other class would always say when I teach organic chemistry. This hydrogen is donated. The other hydrogens are not. It has to be a double oxygen. If it's only one oxygen, like an alcohol, it's neutral. It's not an acid. It has to be both oxygens have that very polar part. Now, for bases, organic bases, I'm going to have a shadow. Let's see if that gets rid of my shadow. You can still see me. An organic base is, again, carbons and hydrogens, and then it's going to be the nitrogen. So nitrogen, when you see nitrogen, and it's something in the PowerPoint I made for your lab that is for Monday, nitrogens love to be bases. And the reason is nitrogens make 3 bonds. But if you look at your periodic table, this is the sad part about being at home. I don't have my nice big periodic table to point at, but nitrogen is in the 5A family or in the 5th family. So they have 5 electrons. So 3 of them they're sharing, and then they have this lone pair. And that lone pair is what is the proton, which is positive, is attracted to that negative electron pair. And so nitrogens act as bases because of that. The nitrogen may show hydrogens on it, or it might not. That has a lot to do with organic chemistry that I am not going to get into. When you take organic chemistry, you can finesse that. Yeah, but when you see nitrogen, you're thinking base. So acids in organic chemistry, we'll see that, or an acid, we will see this, and we will see examples as we're going through these notes, and I'll be able to point it out. Yeah, if you have questions, just ask. Hopefully I can hear. I'm gonna erase. So I erase with a squid hat, for those of you who are new to me, because it erases. Everything else in my house doesn't. A few more terms, and again, I'll run through all this again tomorrow, because we want to make sure we're using the terminology correctly. And then we keep building on this over the next couple of weeks. Acids, this is where that term comes in, monoprotic. So prot means a proton. That's the hydrogen ion, it's a proton. So mono would mean that you only have 1 hydrogen to donate. So our examples there would be the HCl, there's only 1 hydrogen. Or if we did our organic acid, so I'll just make one up, C6H5CO2H. This has only 1 hydrogen to donate. So even in the formula, there's 6 hydrogens, there is only 1 hydrogen to donate. And I wrote it like that. Sometimes you will see they'll write COOH, and sometimes you'll see they write CO2H. It's the same thing. Don't get caught up on stuff like that.
Your camera's a little out of
polyprotic.
focus.
Yeah, the camera's out of focus.
I'm pretty sure you all know poly means 2 or more hydrogens. So an example there would be H2SO4.
Dr. Sherpa?
So there's 2 hydrogens, or H3PO4. So it's just a term.
Dr. Sherpa?
When we do equations on the next page, we're going to look at 1 or 2. You only donate 1 at a time before you start donating more than 1. My camera is out of focus.
Yeah, Dr. Sherpa, we're having trouble reading what you're writing.
All right. Don't know why I can't hear you. I know why. Somebody say something.
Hello?
Is it still out of focus?
Yes.
So there is, I'm gonna pause the record and hope I don't have to splice. Look, it went into focus as soon as I said I was gonna pause recording.
Can you hear everyone?
It's in focus now, isn't it?
It is in focus now, yes.
Okay. Yeah, the camera has a thing. I need Joey to fix that. For some reason, when I switched computers in the past month, it reset to the factory settings. Is it still in focus? And I know the sound had been turned off in here.
Yeah, it's still in focus right now.
I am hoping I'm recording. Oh well. right, next term. Thank you. Who just told me, well, hopefully, and if it's not in focus now, I can hear you. Was there a question up to this point before I go into Amphiprotic? All right, so Amphiprotic, I'm giggling to myself because I have 25 years of teaching this and how people interpret it. So again, we see the proton there. So it has to do with hydrogen, and it's this word, or this prefix, amphi, which you all know because of amphibians. They are switch hitters, is basically what it means. So an amphibian lives in the water and then lives on land. If you're ambidextrous, you can write with both your right and your left hand. When I took trigonometry was really easy for me and I was really bored, and so I became ambidextrous because I did the whole class left-handed because that was the only way I could stay awake. But that was like a long time ago, and so my left hand has lost its ability. When I went to Duke University, that's where I did my graduate work. It's Research Triangle Park, and NC State, UNC, and Duke all are really great basketball teams. And so Duke was playing NC State, so it's a big rivalry. But Duke's a private school. I went there as a grad student, so they paid for me. And NC State was the city school. And we were playing them that night, and the player from NC State said, I can shoot with my left hand, I can shoot with my right hand. I'm amphibious. So don't use the word incorrectly. Anyway, amphiprotic does not mean that the substance can live in the water and on the land. It means that it can donate or accept hydrogens. My story is kind of like, all right. So it can be an acid or a base. Amphiprotic means it could be an acid or a base. As we go through the examples, I will point out things that are amphiprotic. The amphi means it could be one or the other. It is always one or the other in a specific example, but in one example it might be an acid, in another example it would be a base. These three here are not amphiprotic. HCl is always an acid. These guys, these organic ones with the CO2H, they are always an acid. H2SO4, always an acid. And actually, I will do my example here with H2SO4. And it goes into the next piece, next several pieces. If we put H2SO4 in water, so the acid doesn't donate its hydrogen unless there is something else present to take the proton. And so you need the water there. So we're implying that this is aqueous, which means it's in water. So the hydrogen, and when I'm writing these equations, you'll see me circle my hydrogen to make sure you're all following. The hydrogen gets donated to the water. And that's because this is the acid. And I'll just write it as A. And so in this case, water is acting as the base because it's going to accept the hydrogen. We put our arrow. This loses only one hydrogen. So when we do our reactions, they're really easy to balance because everything's going to be ones. So this becomes HSO4. Because it lost a proton, it now has a charge. And that is a negative charge. So HSO4 negative. The H2O has picked up a hydrogen, so it becomes hydronium. So H3O positive. So that's the hydronium ion. The HSO4 negative, this guy can be amphiprotic. It has a hydrogen, so if we combined it with a base, it would give up that hydrogen. But, so that would be the acid part. It has this negative charge now. And so that negative means it could technically pick up a hydrogen. And we go back to where we started. And anyway, that's the idea. We'll see more examples as we go along. It's not a big deal. It's just if we run into the word that it is not too scary of a word for you. We're going to always label our equations. What you start with is your acid base or your base acid. Sometimes I show the base first and the acid second. Doesn't matter. They're your reactants. The products, the acid becomes what's called the CB. And CB stands for conjugate base. So, sorry. Conjugate means the pair. The acid, when it gives up a hydrogen, it becomes a base, and we call it the conjugate base. When the base picks up a hydrogen, it becomes an acid, so we say it pairs with it. So Ca stands for conjugate acid. And you're going to see me using those abbreviations, conjugate base and conjugate acid, as we go through some of the problems on the next page. And just to make sure you kind of have the idea. Let's do a quick example. Leaving Amphiprotic up there. If you had, let's say HCO3. This guy is amphiprotic. Again, it has a negative, so it can pick up a hydrogen. And it has a hydrogen, so it can donate a hydrogen. So it's amphiprotic. It could be either one. It depends on what you mix it with. If we want to make it into its conjugate acid, that would mean it's starting as a base and becomes a conjugate acid. And the base is going to accept the hydrogen, so it would become H2CO3. When you pick up the hydrogen, you'll lose the negative. Don't get overwhelmed by the charges as we go through the practice. That's a small piece of it. So you start with the base, picks up a hydrogen, and now it's a conjugate acid. If we decided it was an acid, it's going to become a conjugate base. So the acid would donate, maybe I should write that. The proton, here it's going to accept the proton. So when it donates, we lose the hydrogen, it goes to somewhere, and it becomes carbonate, CO3. And now we have a -2 because it lost that hydrogen. It was a -1, it lost another hydrogen. And again, what I have there on the note, it always, the conjugates, this is the conjugate base, it differs by 1 hydrogen. This is the conjugate acid. This is our starting point in each case. These two, they look like they're related, but they are not conjugates because they differ by 2 hydrogens. So in acid-base, conjugate acid-base, those two are not, this are not pairs because there'd be 2 different. All right, let me see what's on my next page. All right. The word at the bottom is strong and weak acid, just real brief. Strong acid. One-way reaction. So strong acid, you're only going to see 1 arrow. And there's a reason I mentioned we do acids and bases after we learn equilibrium, because the vast majority of this would be also for strong acid and strong base. Weak acid or base is a 2-way reaction. It is going to be in equilibrium. We're going to have K values, and they are conveniently called, so this is an equilibrium. And so we're going to have a Ka or a Kb. Ka is when you're talking about an acid, a Kb is when you're talking about a base. So like you had KPs in the previous assignment, that's when we were working with pressure. Ka is acid, Kb is base. All right, shoot. Oh, the strong acids. There were classically 6, and then people keep adding and changing. And I mentioned that because in the past, especially when I was live, everyone just went with what I said, and now everyone's looking up everything online and everybody says different stuff. There were classically 6, and depending on what website you look at, they leave one of them off and add a different one, but we're gonna go with the classic 6. HCl, HBr, HI. And the book I posted, or the one that you showed me yesterday, Janae, these are the 6 that he talks about in his book. HCl, HBr, and HI are strong. If you have a periodic table in front of you or you haven't memorized, why isn't HF there? It's not. HF is a weak acid. So these 3 are, and then the other 3 are HNO3, nitric acid is strong. It just means one way. They completely donate. So completely dissociate. That's the word I've been looking for. So we talk about acids as dissociating, not ionizing, because the water has to pull them apart. HNO3, H2SO4, and then HClO4. HClO4 is actually the strongest of them all. There are classically 6 strong bases. They are not very common, so we're not going to worry about them. For most students, they just think of hydroxide. The weak acids and bases are the other quadrillion acids and bases that show up. So we, of course, are not going to make a list of a quadrillion compounds. How you recognize these are acids, they all start with hydrogen. So when you are talking about inorganic acids, not carbon-based acids, we always show the hydrogen first to say, hey, this is an acid. This is extremely useful. On the alchemist periodic table, acids and alkaline were actually present there. All right, so this becomes important as we write our equations and as we get into the math, and that's what I want to do, unless there's a question. And I'm going to assume there's not. All right, so I'm on page 12, which is the acid-base reaction. And again, this is why I do lectures over 2 days. We'll come back as we do practice, and we'll go back over this terminology tomorrow. And it will start making more sense, as everything does, when you start seeing the examples. So all I did was I made a list of my strong acids, and that's the abbreviation everybody uses for strong acids is SA, SA, capital S, capital A. You can take a wild guess of what the abbreviation is for weak acid, which is WA. So capital W, capital A means we're dealing with a weak acid. So you'll see me doing that, and online, I'm pretty sure the videos probably do that. All right, I'm just going to go through 2 of these reactions and then move into the math. And then tomorrow we'll come back and look at the other ones. And if you want, you can even try them at home. And then as we go over them tomorrow, you can see how you did. All right, the reactants will be given to you. And what you need to do is label which one's the acid and which one's the base. Unfortunately, in my first example, I gave the acid first. And so some students assume the acid is always first. That's not a rule. But you don't want to just say A, you want to label that that's a strong acid because it's in our list. And that's important because your next step is your arrow. if you look at the next question, B, let me put it up here. We see a CO2H. So this is a Wa. It's an acid, but it's not one of the strongs. And so that means 2 arrows. And so that's actually really important because when we get into the math, this is old school math, one direction, and this is all our equilibrium math with K expressions. All right, acids don't react with other acids. It's always an acid and a base. So if this is my acid, in each case, the other one must be a base. And then we finish it. I'm going to do the thing where I circle. You don't have to do this. It is something that helps a handful of students, maybe more than a handful. So the hydrogen is donated by the acid to the base. And again, sometimes it shows the base first. The arrow will go the other way. So over here, the acid lost 1 hydrogen, HSO4 negative. If you lose a hydrogen, you now have a negative to show that loss of proton. This is called the conjugate base. So an acid becomes a base. They always complement that way. The NH3 picked up the hydrogen. Now something I wanted to show you, whenever a nitrogen picks up a hydrogen, we always show the hydrogen after the nitrogen. It's just with nitrogen that we do that with. And especially when we get into the organic ones, you show it after. And because this picked up a hydrogen, picked up a proton, it now has a positive charge. And this is called the conjugate acid. And it's so simple when your teacher does it. That's what we're going to do 2 today, so you see it, and then we'll do more tomorrow, and then some show up in your homework and other places. All right, it is helpful, only this hydrogen is donated. In the organic acids, it's that double oxygen H that makes it a weak acid. And so we will get CH3CO2 gets a negative because it lost a proton. And the H2O picks up. So you show it with the other H's, and it's now a positive. So what you need to do is label your conjugate acid, conjugate base. So which one is the conjugate acid, and which one's the conjugate base? So go ahead and label them. I'll give you a moment. So the acid becomes a conjugate base, and the base becomes a conjugate acid. Because in this equation, since it goes both ways, if we were looking in the reverse direction, then the H3O, the hydronium, is acting as the acid, giving the hydrogen back to the acetate, and we come back to the beginning. Your reactants are always the acid base. Your products are always the conjugates. And we'll do these other ones tomorrow, the rest of this page. So I'm going to move on to the math. And maybe, unless there's questions. And I'm not seeing any questions. Sorry, I can't, when I have my glasses on, you guys get this crazy reflection, even worse than right now. This is my page where I usually talk for a half hour about acidosis. I made a video about it to save on time, and you can do a whole lab. So hopefully you had to start the lab by today because it's due next week. So there's that 7-day challenge in there. But it is an article I read over 20 years ago. And it was actually in an acupuncture journal. It was from a guy at UCN SF in San Francisco. And he just talked about that we were in chronic acidosis, this country, and due to our diet and our lifestyle and stuff. So we'll keep coming back to that. And also for that lab, you do get to watch one of those videos over the weekend, and also try some new recipe out. All right. And have fun with it. So I'm on page 13, and if you don't have your calculator, pause me and get your calculator, because we're going to do calculations. Or you're going to do calculations. I've already done my calculations. And I'm going to erase this unless somebody had a question. Apparently. You can always ask later or tomorrow when we come back and fill in all the blanks. So the idea of pH is actually only about 100 years old, which actually blew me away when I learned that only like 2 years ago. I'd never actually thought about it, because you learn about pH when you're a small kid. Everybody's like heard of pH. Couple things about it. So it was Soren Sorensen came up with the concept of pH because it made it much easier to discuss acids and bases to use the scale. And it is always a small p and a capital H. So please don't write it like this, because that's something that drives chemistry teachers crazy. That's like if you get a doctorate, if you're an old fuddy-dud. It also means piled higher and deeper. So if you want to get into a real good discussion, trust me, I can pile it higher and deeper than all of you. All right, so little p, capital H. And what this little p stands for is negative log. And this is LOG log, log base 10. I mention that because you all took Chem 222, and in kinetics, you do a lot with natural log, LN. So just be careful, we're doing log base 10. And the H is hydrogen. But since we're in chemistry.
Okay.
Oh, sorry, let me finish this and then I'll answer your question, Janae.
Never mind, you were just blurry, but you're fine now.
Yeah, you know what it is? It's the camera is an autofocus, so it sometimes takes a moment. And so if I move around too much, it tries to find me instead of the board. So I have to take it off the autofocus on this computer. So usually if you've learned pH before, which I'm sure you have, you learn it as the negative log of the hydrogen ion, which is great. Technically it is, again, the hydronium ion, because we don't have protons roaming around by themselves. They combine with something. Protons are usually very deep inside the atom, right? That little speck in there. And so they have this gigantic, enormous castle that they can be safe and sound in. And all right, there are other P scales. There is the Poo scale. So little p, capital OH. So little p always stands for negative log. And then OH stands for OH, hydroxide. Now this scale fascinates me. I mean, one, chemistry has a scale for everything, but I actually never learned about the Poo scale. It is not actually pronounced poo. It is pronounced POH. I think it was something that was made up since I was in school. I know everybody knows about it, but it's really not used except in like learning chemistry and doing the math. And so we're going to use it because we're in the point where we're learning chemistry and doing math. The other thing I wanted to point out, because I can tell you another one of my little stories, true story. It is read as PH and POH. So it is not, you don't read it as a scale. And I tell you that because when I was in graduate school, some salesman came in and he was trying to sell something. And everybody's like, oh yeah, talk to Joyce. She's the one who would need that. And I was in the middle of doing something, very busy, very busy. And I said, just give me 5 minutes. Well, it was a young man, and a young man sits there and sees a young lady, and he can't just stand there quietly for 5 minutes. He had to talk to me for 5 minutes and make like random conversation, and the pH meter happened to be next to me, and he said, oh, who'd you buy the meter from? And I stopped what I'm doing. Everybody in the room stopped what they were doing and looked at this guy saying, did he just call that a meter? And so then I had a 20-minute conversation about our amazingly fantastic meter, and nobody ever bought anything from this guy. So even if you become a salesman, don't call it a scale, it's a pH scale. All right, that's my story. Usually it gets lots of jolly laughs and stuff, but since you're all muted. I'll pretend like you're laughing. The reason for this scale is it goes back, I'm doing this kind of backwards. It goes back, why Sorensen came up with the scale is that in any solution, if you take the hydronium concentration times the hydroxide concentration, so brackets, when they're square like that, that means that this is molarity. It is the concentration of the hydronium and the hydroxide. Now, with that said, I showed really nice brackets. You guys are probably going to see me use parentheses. I'm okay with parentheses. I know I mentioned that with equilibrium too. It is technically brackets. Anyway, this is always equal to 10 to the negative 14. This is called capital K, W. The W stands for water, because if you have, you don't have to write this down. This you do need to know. We're going to use it. If you have water and it reacts with itself, which believe it or not, this is going on in all of your bodies right now, all over the place. Which one's the acid? Doesn't matter. Call the first one the acid. That one's then the base. Because water is amphiprotic. This water gives up its hydrogen. It's not one of the strong, so we showed 2 arrows. And we get, hydroxide plus hydronium. So this is going on in every cell, every part of your body right now because we are water-based. But this Kw is a really small number. So this reaction is mostly in the reverse, a little bit going forward. So there's always, in every solution that is aqueous, there's always a little bit of hydroxide and a little bit of hydronium. Whichever you have more of determines if it's an acid or base. So if they are equal, you're neutral. If you have more hydronium, then you're an acid. If you have more hydroxide, then you're a base. And it gets really tedious looking at these numbers. And so Sorensen said, hey, let's make up the scale using logarithms. I've actually only had one person ever pick him as their famous chemist. And it was an awesome paper because they were able to really relate it to the class and they were really interested in some of the stuff he did. So if you don't have a chemist yet, there's a couple others that we've run into in these notes that might give you an idea. So this formula is a way that you can always, if you know hydronium, you can find hydroxide. If you know hydroxide, you can find hydronium in this formula. So those two have to become second nature. You don't, you know, even though you guys are all on computer and I don't know if you have a note card or not, you have to know it like that. And we use it so much over the next 2 weeks, you're gonna know it better than your middle name probably. The POH is gonna be very useful to use. And I'm gonna do a really quick algebraic magic thing. And some of you are really good at math and you're gonna be like, oh, of course. And some of you are like, what? But it is something like in Math 111 you learn, if you log this whole equation, you end up with pH plus POH equals 14. And that is the magic of Sorensen, that we get rid of this crazy exponent that you're gonna see we're gonna run into for the next 2 weeks, and we make it numbers. That just 14 instead of, and all of you have had this, even those of you who are like in Math 5029, that you all make a calculator error. Whereas when you're working with the number like 14, that's easier to put in your calculator. And the brilliance of the pH scale is when you have a pH below 7, you're an acid. When you have a pH above 7, you're a base. And when your pH is 7, you're neutral. All right, a couple other things about the scale. It is a log-based scale. So a change of 1 in the pH is actually a 10-fold change, because that's why it's called log base 10. So it's like the earthquake scale. Every one place higher in an earthquake is 10 times more powerful, and so it causes like exponential more damage. These two equations that I did not circle, you're going to see me using them because they're really useful tools. But these two that I circled, you can get to every answer just with those two formulas. All right, we're going to walk through. I'm going to walk through A today, and then we're going to move on. Oh, we'll walk through A and B. All right, question.
Not for me.
Thank you for doing that sound check for me. All right. So my question says you have 0.50 molar HCl. Oh, nope. Right, be careful you get your place value right, because that will make a tenfold difference. And it wants to know what's the pH. The thing that's important here is back to over here, my list. HCl is a strong acid. So since it's a strong acid, strong acids mean this is your hydronium, because they completely dissociate. So that's my little note up above there. Whenever you see a strong acid, you just write your formula. And then you just solve. And then you punch it in your calculator and you get my answer, which is 1.30. Extremely acidic. We would expect it to be a really low pH. The lower the pH, the stronger the acid, because it's a strong acid. That would burn. You want, like if we were in lab and this got on your finger, you wouldn't calmly walk up to me and say, oh, Dr. Sherpa, I spilled some on my finger. What should I do? You would immediately have gone to the sink and started rinsing your hand because your instincts would take over. There we go. So a comment about sig figs while I'm thinking about it. Log is a function and all the sig fig rules change. And it is this number 1.30, how I have it written, has 2 sig figs. No, it's an optical illusion. It looks like it has 3, but it is only the place value that counts when you do a log function. So my recommendation for you, it was something came up in office hours last night and today. Somebody said, you know, do you dock a lot of points for sig figs, blah, 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 blah. I go with the rule that you learn when you take physics. If you give all your answers with 3 sig figs, just 1.30, and go with it this term, we should be good. There is an exception to that. I recommend that you always report pHs to 2 decimal places. And that will become important next week when we do buffers. All right, there is a second half to this question, and it says, what is the hydroxide? So whenever you're solving and it is show your work, always state your formula. By stating your formula, it will also help it ingrain into your brain so you can do this. It becomes second nature. So as we get into buffers and titrations next week, this is all very fluid. The hydronium times hydroxide equals the magic number 10 to the negative 14. So we would plug in our hydronium, 0.050. Hydroxide would be my unknown. You can call it X if you want. And that equals 10 to the negative 14. And you would solve. So what I would need to see is the formula you're using, how you plugged in, and your answer. If you want, you can show me how you solved. That's kind of a personal thing. Some students like to show their math, and some of you just can see it. So my X, this is the other thing, and you'll hear me say this constantly over the next 2 weeks. Once we get into acids and bases, don't just label things as X. Always tell me, what does the X mean? My X is my hydroxide. And so it's whatever my answer is. It should be 2.0, yeah. Whenever you're solving for hydronium hydroxide, it is capital M, which is molarity, moles per liter. And so this is just a basic problem showing you how to use those formulas. We're going to move on to the next page and apply it to equilibrium. But I actually do want to look at number 2, or B, and talk about P's for a minute. All right. So it tells you P's have a pH of 3.65, and it wants us to find the hydronium and hydroxide. So I'm just going to find the hydronium, and then from there you can find the hydroxide, and we'll do more with this tomorrow. This question, though, is the opposite of question A. On question A, we were solving for pH. So we use that formula. In this question, we're given the pH. So about half of you have the fancy calculators. I have like the simplest calculator. And you'll just still use this formula and say 3.65 equals negative log of X, solve. And you'll get the answer, which is great. Don't go and buy a fancy calculator. To change this so we can solve, the opposite, like when you're adding, the opposite of adding is subtracting. So in algebra, to rearrange this formula, the opposite of log is 10 to the power. So what happens is we first move our negative to the other side and we get negative pH. And then we do 10 to the power to get rid of the log. So 10, put the little caret to the negative pH equals your hydronium concentration. So that is a really handy formula to also know. That's why I bracketed it there. If you're given pH, that's going to be your first step for like the rest of the term, the rest of your life. Given the pH, you can figure out your hydronium. Real quick, before we move on, there is often a misidea, for lack of a better word, that students believe the pH scale goes from 1 to 14. It doesn't. It can actually, you can have a pH higher than 14. Here's a question to ponder. If you had something at a pH higher than 14, it doesn't go much higher, but let's say a pH of 15, what would that mean about the substance? You can also have a pH below 1. You can actually have a negative pH. So if you had a negative pH, what would that mean? So something for you to think about. One thing it would mean is serious caution, because it's extremely acidic if it's a negative pH. And above 14, you're extremely basic. But my answers are there. And again, if you want, you can look at these tomorrow. I'll go over the rest of the page or answer questions that you have on that. But I'm going to move on, because I want to talk about weak acids and equilibrium before it becomes 100 degrees in this room, because the door's closed and it's like a tiny room. And all right, any questions before I erase and move on? All right, so page 14, for those following along in the virtual world, which is all of you. All right. I'm going to show you where this formula comes from. You don't have to write this equation out. If you have a weak acid, this is just like the generic weak acid. It's like the generic drugs that everybody, generic aspirin, it doesn't have a name. The hydrogen is going to be donated. The A could be any formula. And if we put it in water, the hydrogen is going to get donated to the water. It is weak, So two-way reaction, equilibrium, those beautiful arrows. And we end up with A negative, which is the conjugate base, and H3O positive, which would be the conjugate acid. It is a two-way reaction. I didn't label the water for one reason. We can write a K expression because we have equilibrium, and it is called K little a for acid. Products, A negative times hydronium, and then over HA. And I leave the H2O out. So the question is, why did I leave the H2O out of the K expression? And this was a question that Baker had asked me earlier when we were going through homework questions. And it's something I want to remind you. It's a liquid, and we don't include liquids in the K expression. It is needed for the equation to be balanced. Everything else, ions are always going to be aqueous. Acids and bases are aqueous. So that's where this formula comes from. There is an easy way to write it, because writing Ha and A negative looks like an A minus, and it causes anxiety because you're like, no, I'm an A plus student. You can instead just write Wa for weak acid, and here you can write conjugate base. So I'm just using my terms down here instead of the symbols. And then you can plug in any weak acid, any conjugate base. We use, this is like given to you in that big box because we use it. We use it a lot. If you were doing this with a base, let's just write weak base plus water. The base is going to pick up the hydrogen. The water in this case is going to be an acid. It's weak, so there's two. And again, you don't have to write this down. Some students will write it down because it helps them. But I wanted to show you where our formula is going to come from. The weak base would now become a conjugate acid. So the base becomes a conjugate acid, and the water lost the hydrogen, so it becomes hydroxide. You can ponder this. We can talk about it later. I want to move on right now. In all honesty, you don't need to write these equations out, the reactions, the chemical reactions. Learn this Ka formula. And I know a lot of you go to other websites. I've done this long enough. This is the easiest way to do everything we're going to do for the next 2 weeks. This is how I'm going to be teaching it. And having done this for a long time, this ends up working because also when I ask you to explain stuff, this works great. A stands for acid, Kb, without writing the equation. Acid and base, right? The yin yang, they balance each other. Instead of saying conjugate base, it would be conjugate acid. Instead of hydronium, we would think hydroxide. That's negative. Instead of weak acid, we think weak base. So if you know the Ka formula, you know the Kb formula. And then there's another thing that's in the bracket there, and I'll talk about it more tomorrow, that if you have a Ka and you multiply it by Kb, it equals Kw. If you're curious how that works, I can show you. I'm not going to spend the time here in the recording. This is for the weak acid, and this is the Kb of its conjugate base. So it can't just be any Ka and any Kb will always equal Kw, which is 10 to the negative 14. It is specifically the Ka of a weak acid times the Kb of its conjugate base always gives you 10 to the negative 14. All right, I want to mention one more thing, and then we're going to do one problem, and then we'll be done for today. And it's to see, because I'll probably forget tomorrow to mention this. What if I gave you the term little p Ka? Little p, capital K, and then subscript A. What does that mean? Well, what does little p mean? Anytime you see a little p, it just tells a scientist, oh, negative log. I'm going to do negative log. I'm going to do negative log of the K8. You don't have to remember that, because if you understand what the little p means, you know it. And so then, of course, there's a PKB. There's a P. There's other ones too. All right. I mentioned that because I usually forget, and then it shows up on the first page of the homework. And then students are like, oh, what is this? All right, we're going to do problem A. And then maybe we'll do B. We'll see. Yeah. So if you guys have questions you would have like, or you can also ask after, or you can ask tomorrow at the beginning and say, hey, can we go back over this? I'm going to go through all these pages tomorrow. Yeah, and the last 2 pages are charts to go with what we're going to talk about here. So it tells us calculate the pH 0.15 molar HF. And then it says, oh, by the way, the Ka equals and then it has the second part. I said to write a note to myself, or else I'll forget to do this. All right, the last 2 pages of your notes. And then real quick, for those of you listening at home, I usually get somebody who asks at this point going, what notes are you talking about? There are notes that are posted under handouts on Blackboard, and so that's what I'm following along with. Again, this class is very much problem solving in 223. And so I'm giving you the problems so you can, if you print them out, you can just take notes as we're going along. The last 2 pages of the notes are charts from that book that I posted that have Ka values. Most of the time, obviously on a quiz or a test, I will give you the Ka value, but when you're doing homework, please use these charts. Kas can be different on different websites. And then that gives you different answers than me and everybody else. And then it can cause some confusion for people. And it is because it's back to sig figs. And back to the lesson, way back when you learned 221, it was like your first lesson was sig figs and they're so tedious. Kas, anywhere you see them, only ever have 2 sig figs. Same with KBs. And that is because they're very imprecise. You can only really know them to 2 sig figs, as opposed to the mass of the electron, which is known to like 18 or 20 decimal places now. Kas are very imprecise. This is a generalization we're making, and anyway, go with that. So this way we all can have the same answer. So if I give you a problem, you know you need a Ka because this is not one of the strong acids. So since it's a weak acid, we have to solve with Ka. Strong acids are one way. Weak acids, which is again the quadrillion, everything except these 6, which is pretty much everything, you have to use equilibrium in chemistry. Whenever you solve problems and show your work, you want to first state, this is all formula based this term, you want to state the formula you're using, and it's going to go to this formula that's at the top of the page. You can write acid, or you can write Wa, or you can write HF, I don't care. But state the formula. All right, and then we're going to plug in. So how do I know it's x squared? Because these are all going to be x squared, which is wonderful. That makes this the easiest chapter we do the whole term, is working with weak acids and weak bases. What we do next week when we get into buffers, it's not x squared. But I want to write out the reaction that is happening to show you why. You do not need to write this reaction out because you're not going to have to. This is just saying if you take a weak acid, for it to be an acid, it's aqueous, which means it's in water. Back to Sorensen and all the alchemists before him, there's always a small amount of it that is ionizing, but it is a two-way reaction. So this hydrogen comes off, and we end up with F negative, and H2O becomes hydronium. So F negative is the conjugate base of our weak acid. If we did an ice chart, so this is the good news, this is my recommendation, no ice chart with this lesson. We get back to them next week, and we have them with the lessons we just did. But if we did an ice chart, I'm going to show you why you do not need to do an ice chart today and tomorrow and Friday. Is I know my initial of my HF. And again, this is why you don't have to write this down. You can just say, okay, I got it. Appreciation. H2O we ignore because it's a liquid. F negative and hydronium. Initially, they're at 0 because initially you're putting the HF. It's about to ionize. This is going to change by X. So this will be 0.15 minus X. And these are both going to increase by X. Since our balanced equation is all ones, we don't have to worry about 2 X's or anything. So technically, this should be 0.15 minus X. The numerator, they are always going to be equal in this chapter. Again, when we get into buffers, that's not going to be true. Next week, that's after the midterm. Don't worry about that next week. It's going to be present now. So the real question is when I wrote it, I ignored the minus X. And you can too. Only with this. Because weak acids are weak. Their K values are always small. And so X is always going to be itty bitty. You would have to have 4 or 5 or 6 or 8 or 10 sig figs to be able to see a change when you subtract the X. And then when you do the log thing, it doesn't make a difference. And so we ignore the minus X. That's what my little note to you says, and I lost my page. Oh, there it is. Right. There it is. So this is you state the formula, you set it up. And something you're hearing me say tomorrow. I said it earlier, so somebody hopefully is saying it, but I can't hear you because you're all muted. Don't ever just say X. Whenever you're working with acids and bases, tell me X equals, and it is hydronium. Because some of the times it's going to be hydroxide. So how do I know it's hydronium? Because it's an acid. Because it's a Ka. If you look at question B on this page, it's nitrogen. Big take home message. You see nitrogen, you're thinking base. When we do KBs, you're going to solve for hydroxide. So there'll be an extra step. All right, you solve for X. I'm just going to give you my answer. You can try this at home, whether it's today, tomorrow, the next day. That's my value of X. If I do the negative log of the hydronium, and this is a shortcut I do allow in your show your work. You state your Ka, you state your setup, you tell me what X equals, and you're going to tell me you're going to do the negative log of that. You can put an arrow and say, I'm just going to plug that in there. You don't have to write it out again. So the arrow is a wonderful trick. This equals your pH, and the answer makes sense. because it's an acid, the pH needs to be less than 7. This is actually a fairly strong weak acid, so it's a fairly low pH. If it's even 6.5, that is an acid because the pH is less than 7. So like if you look at C, my answer is 5.83. That still makes sense because it's a weak acid, the pH should come out less than 7. Whereas if you look at my answer for B, something again we'll talk about tomorrow, it's going to be a base, so our pH should come out above 7. All right, let me do the second half of this problem so I remember to do it. And then it's a lot of information. What I'm going to tell you, having done this, a lot of students leave today with their eyes wide open going, oh my gosh, this class, there's a lot of information. By the time tomorrow's done, you're going to feel pretty good with this because we're going to go back and go through all of it again and fill in all the pieces. We have a couple more things we have to add. So if you're somebody, and this has actually been amazing, I've never had this happen before, and I think it's because of the environment we're all in this universe right now. Usually nobody even looks at this homework set until after tomorrow's lecture, but a lot of you have been like staying on pace and even staying ahead. There's like the 3rd page of the homework set you need in tomorrow's lecture. I would recommend not to try it until tomorrow's lecture because there's a twist that happens that I'll talk about tomorrow. But you could definitely, if you wanted to get ahead, you do have a lab due tomorrow. You can do the lab that's due Monday and get it out of the way. You do lots of stuff. And then once we get through tomorrow, the homework set, once we get through both lectures, the homework set becomes pretty straightforward. All right, the second part of the question asked us, I can do it here, to solve for the percent ionization. Simple formula is change over initial equals the percent. So if you remember in question number 1 on your worksheet that's due today, it was initial times percent equals change. The other way students will write this is X over the weak acid equals the percent. So it means your hydronium number that you solved for down there divided by the original acid times 100, because it's a percent. That will give you your percent, and that's where I got my answer from. So it comes out just under 7%. It's telling you how much of the equilibrium, how much of it pulled apart. One last thing. This is a terrible question because acids do not ionize. I mentioned this. They dissociate. The water pulls them apart. But unfortunately, somebody called it percent ionization, and it stuck. And so we should say percent dissociation. And I think for a couple of years I used to call it that, and it didn't catch on. So as opposed to my term, the Fiercebo effect, that's catching on. All right, we'll talk about that eventually. Is there questions for me before I stop recording? Hopefully I'm recording. Or I can stop recording and you can ask.